Well, when you're seeing a title like this, Technical Controls for Securing Data, you might be wondering, well, isn't this all that CySA Plus is about? Isn't this what we've been talking about so far? Well, yes, and this chapter does have a kind of a recap flavor to it. But we're also going to focus specifically on controls designed to protect data and nothing more. All right. So it's nice that we have policies and procedures in place, but since attackers don't really play by anybody's rules and policies, we still need our defenses to be up. So let's see what technical defenses we can use to defend our castle that holds data, of course. And when we say technical controls, we are referring to things like systems, hardware, software, appliances, physical or virtual, even configuration items and specific types of configurations that help us make our environment and our network and our users and our data more secure, right? So most of them do this by minimizing exposure. So we're trying to reducing the attack surface. And the central idea here is that we are doing it by relying on technology. That's why we call them technical controls. And when we talk about data, we first have to handle the way data is accessed before thinking about any other kind of defenses. So access control, right, means allowing or denying access to some resources. It mostly is going to involve access to networks or access to specific files or access to databases or to specific tables or entries inside of a database. And generally, when we think about controlling access, we're going to implement this type of control in software in a structure that is called an access control list. Now, the access control list, or the ACL, includes a list of who is allowed to access the resource and what permissions they might have. Each record inside such a list is called an access control entry, or an ACE. And we can apply this for networks. So for network access, they're going to be implemented in the router, the firewall, sometimes even in the switch, depending on what layer you're applying those ACLs. And nevertheless, they're going to block or allow access to the network. That is, they're going to block or deny traffic. But for files and folders, the support for these ACLs has to be built in file system. And luckily, most of them allow ACLs to be implemented, like NTFS on Windows or ext3, ext4 on Linux systems, ZFS on Mac OS, and so on. They all support ACLs. And it kind of applies in a similar manner to databases as well, but with a more fine-grained permissions, like which specific SQL statements are allowed for each user or each database, or which tables or which entries can a user view, or can a user modify or alter or make any kind of changes in there. And access control is one of the first places where the principle of least privilege has to be enforced and makes sense to be enforced. This is how users get just enough access to do their jobs, but not more than necessary. So this is least privilege. Now, controlling access might cover more than just who accesses what, but can go into a bit more detail, such as the geographical location of the user that is accessing the resource, or the time of day when the access happens, or any more complex checks that can be performed. And these are sometimes called either time-based ACLs, if they just take the time of day into account, or context-based ACLs, if we take into account things like geographical location, the posture of the device that we're using, the type of network that you're connecting from, and so on. So we're building a context out of multiple variables here. And these type of context-based ACLs are nowadays found in more modern firewall solutions, like next-generation firewalls or UTM devices. So going deeper, we have to think about file system permissions, right? Because that's where data is stored in some sort of a file system. It might be a database, but let's start with the file system. Now, we mentioned that access control for files and for folders happens at a file system level. So let's see how these permissions look like. And we're going to start with Windows, right? You can view the file permissions in Windows using the File Properties dialog. So if I were to just choose a folder on my disk and head over to the Security tab, on the bottom half of this window, I'm going to see the permissions for authenticated users. And you can see that the type of permissions that we can enable in Windows belong to the following categories, starting with full control, right? This is going to allow users to read, write, make changes, delete files and subfolders, Additionally, users can also change permission settings, so they can override these permissions by their own free will, right, for all the files and subdirectories. Next up, we have the modify permission. This one allows user to read and write files and subfolders, also allows a deletion of the folder itself. Then we have read and execute, allows user to view and run executable files, including scripts. Don't forget about this one. List folder contents, I believe this is already obvious what it does. Allows viewing and listing of files and subfolders as well. And this one is inherited by folders only, because it only makes sense at the folder level. Next up, we have read permissions, allows user to view the folder and the subfolder contents. And finally, the write permission, last one here, allows user to add files, add subfolders, create content, basically allows you to write to any files. Now on the command line, you have the command called icacls or icackles, how it is sometimes pronounced. This tool can be used to display the same information and change the permissions if necessary. The icackles tool does use some shorthand notations, and you can see them all here on the slide, but we're basically talking about the same type of permissions that we can view in the graphical interface of Windows as well. Now the icackles command just by itself is going to list all the possible permission combinations, right? So make a note of what's the shorthand notation from the icackles perspective. Or if you were to list the permissions for a specific file, let's say for example that I'm interested in the permissions on this PowerShell script right here, right? It's going to tell me that the system user has full permissions. Administrators also have full permissions, and also myself, which I am a member of the administrators group, will inherit the full permissions as well. Now the I at the very beginning, let's scroll up here. I'm going to see that it belongs to the inheritance section right here. It says that permission is inherited from the parent container, right? Which basically means the parent folder. And of course, you can use this utility to change the permissions if you are allowed to do so on the files and folders where you have full access or you are the owner of that data. Linux, surprisingly enough, is a bit simpler than Windows. Only has 3 basic permissions. We have a read permission, which means reading from a file or list the contents of a directory. Writing means modifying the files or creating files, renaming them, deleting them inside of a folder. And execution, this means the ability to run executable programs and scripts, or importantly enough, the ability to navigate into a directory. So changing into a directory using the cd command in Linux is considered an execution of that directory. So you need execution permissions on that directory to be able to change to it. Just a small caveat. And we also have 3 basic permissions, and these 3 basic permissions apply to 3 types of entities. We have the user, which is the owner of the file, the group that the user belongs to, and anybody else, the rest of the world or others. And each of these entities we're basically going to describe whether they have read, write, or execute permissions. And we're going to describe these permissions in an octal format, that is base 8, not base 10, right? Let me show you what this means. All right, so on a Linux prompt using the ls-l command, this is going to list all the contents in a detailed table, right? So we're going to see there's the first column here on the left. That's going to be the permissions column for each file and folder in the current directory. Now let's choose one of these here. So for example, this file, right, games.txt. The first section here, the first letter here, is actually going to be a line for files and a D for directories or folders. We also have some other indicators here, such as symbolic links, but we're not going to focus on them for now, right? The rest of the permissions here on the right of the first dash are actually grouped into 3 sets of 3 characters. So the first set here tells me that the first one, the user, right, has read and write permissions, but doesn't have execution permissions. It's not necessarily a restriction, but it's simply because a txt file doesn't really make sense to be executable, right? Next one is the group. Now the group is only going to have read permissions. You can see there's a dash for the write and execution permissions. They're absent here. And the rest of the world, surprisingly enough, has read and write access to this file as well. Now this permission set right here can be represented as a binary number. So if you consider that whatever permission is set is a bit of 1 and whatever permission is not set is a bit of 0, then RW dash would mean something like 110, right, in binary. Now if we were to convert this into decimal, we're going to basically have 0 times 2 to the power of 0, that's a 0 right here, plus 2 to the power of 1, and plus 2 to the power of 2. So we're basically going to have here a 4 plus 2 plus 0, which equals 6, right? So the permission for the owner of this file can be abstracted as 6. Now notice that if we were to set all the bits in here, we would get a max of 7, right? We're just missing the first bit. This is why we say that this representation here is in octal format, because we never go higher than the number 7, than the digit 7, right? Now, if we also move forward here, let's say the next set of permissions here, that would be a 4 plus 0 plus 0. So this would make something like, let's have a new line in here, R dash dash. This would be something like 100 in binary. So it would be 4 plus 0 plus 0, that's going to be 4, all right? And finally, the last one is going to be similar to the first one, right? So it's going to be equal to 6. So the resulting permissions, if we're to abstract it, of this specific string right here, could be written as 646, right? And this is the type of permissions that sometimes you're going to see in Linux systems that is even used as an argument to the commands that can change permissions for files and folders, like chmod command. We can use the chmod command to change permissions for existing files. So for example, I can use chmod here to change the permissions on, let's say, this file right here, which currently has a full set of permissions. This would be 777. Right? So let's change this one to 646 for my.sh. Right? Let's list the contents again, this time just the my.sh file, and now you can see the set of permissions matches the one that we've borrowed from the games.txt file. Now similarly, we can also use the chmod command to add specific permissions. So for example, we can say that we want the user or the owner to add, so we're going to use a plus in here to add an execution permission for the my.sh file, right? Let's repeat this again. Now you can see that the X has appeared here under the first set of permissions because the user, right, the first set has received the execution permission on this file, right? So this is how you view permissions. This is how you change permissions in a Linux system. You also have the chown command, as you can see here at the bottom of the slide. Now the chown command is just about changing ownership, right? By default, you're going to see that if a file is created by a Linux user, it's most likely going to belong to a user of that name and an equivalent group of the same name. Of course, you can change this ownership. Basically, this means sharing that content, that file, that folder with somebody else on the same machine. You can do this with the chown, change ownership command. Next up, when talking about protecting data, we have to mention encryption controls, right? They are meant to ensure confidentiality and also integrity. Actually, integrity comes as a side effect of ensuring confidentiality. It's best to assume that encrypted data can be viewed by anyone. Don't hide it anywhere, right? Rely on the fact that encryption cannot be broken. So if the data falls in the hands of bad actors, encrypt it so that unauthorized access will not hurt you in any way. And encryption actually has to address a couple of categories here. First of all, we have data at rest. That is encryption when data is stored on hard drives, on archival media, or in databases even. We also have to address data in transit. How do we encrypt data as it traverses our networks? This is also called traffic encryption and can be implemented using standard methods such as TLS or IPsec or MACsec, right at layer 2. Data in use when the data is loaded into memory by a program and has to be processed by the CPU. Now, this is not always possible, since at some point when you need to use the data, it will have to be decrypted, right? At least for a couple of milliseconds, otherwise it would be unusable. But there are solutions that address these requirements, such as Intel SGX, that is software guard extensions. This solution attempts to encrypt memory contents even as those contents are being used by your programs. Also, don't forget that every encryption method is not necessarily good enough, right? Some algorithms are more secure than others. You should periodically check that the encryption methods that you're using are still up to date and haven't been deprecated, or no vulnerabilities have been found or weaknesses in their algorithms. And of course, requirements for encryption can come from legal requirements or regulations, and they usually address some sort of a minimal level as a minimal key length or minimal type of algorithm for encryption. Don't forget about DLP, even though we talked about it before, right? But as I said in the beginning, this is also a short recap. So DLP, data loss prevention or data leak prevention. So when you're a company that processes data, one of the methods for securing data is ensuring that it doesn't leave your company, especially if it's sensitive information, so it doesn't get in the wrong hands. Now, DLP controls first have to classify this information to determine which type is it. It's like personal identifiable information. Is it credit card data? Is it finance data? Any other custom type of sensitive data? And then it has to monitor any outgoing channels that might leak that sensitive information. Now, these channels can include things like email, web uploads, including to personal email services, instant messaging, of course, social media uploads, or even uploading files to external peripheral devices such as USB drives. So they all have to be taken into consideration to secure data, as in not allowing it to leave your premises, your company. Now, de-identification controls are another category here for protecting data. And de-identification as a general term is a process that slightly alters a piece of data so that it can be shared or used without unnecessary risks to privacy. And we have some methods of doing so. First of all, we have data masking. Simple enough. It's about just replacing some of the data in the sensitive fields with things like null fields or X's or asterisks or something like this. Sometimes it's also called anonymization when the entire data field is masked. It's a method that works well against data exposure, and you might have encountered this method when you are reviewing, for example, an online transaction, or looking at your previous orders, or looking at your saved credit cards in an online store, right? You will usually see just the last 4 digits of the card, just enough to figure out which card it is, but not the rest of the data, without disclosing that sensitive information. It's also great against shoulder surfing, like having someone peeking over your shoulder when you're viewing some private data. And of course, this method is irreversible, right? If you see data masked in a form, in a database, there's no way to extract it from those X's or hashtags. You need to query that information again, perhaps even with different privileges, to get that original data. We also have a method called tokenization, another de-identification control, which replaces data with a randomly generated token value, basically a random binary value or a random string. Now, that token is stored along with the original value, separate from the original database, like in a completely different database. So when you pull data out without the token, as a hacker or as a guest or as a normal user, data is unreadable, right? But when you pull that data along with the token acts as a key for specific fields. So it's like having a password to unlock specifically those sensitive protected fields. The advantage is that this approach is a bit less intensive, like CPU intensive, than encryption. And it also works just fine from legal perspectives. The sensitive data is not stored at all on the primary database. It's not even encrypted, it's simply not there. Another interesting method is aggregation or banding. It's a very simple de-identification technique which simply replaces some specific data, like a number, with some vague broad range, like an age. For example, instead of storing somebody's age, you replace it with an age range, just saying that it's somewhere in between 20 and 30 years. But you're not storing the exact value. Or just a city in place of a specific address. And of course, since we're talking about cybersecurity, we have to talk about de-identification attacks because they're a method to reverse these techniques. Now, these attacks address the risk of correlating in a clever way seemingly irrelevant or completely disconnected pieces of data, so that when they're put together, they allow you to draw some conclusions to determine more information about that sensitive data. So it's not an attack that tries to, I don't know, reverse that token or anything else, because if it's about data masking or tokenization, the data is not there anymore. So no type of attack is going to be able to retrieve it, but it's about trying to figure out more out of a limited set of information. And one final topic here is DRM. It's very likely you've heard about this one in the context of movies, videos, video games, music, ebooks, and so on. And well, DRM was invented not to annoy us, surprisingly, but because data has to be transferred and its distribution has to be controlled somehow, even after that data reaches a customer. So DLP cannot apply here because we cannot block the content. We have to deliver it to the customer. You need to transfer it. And encryption doesn't apply, or at least doesn't apply in a purely, let's say, secure manner, because if we encrypt it and we ship it to the customer, we also need to send the customer the decryption key as well. Otherwise, that data is unusable. So what do we do? Well, DRM attempts to mitigate the risks of a client distributing unauthorized copies of that same content, and several methods have been invented to allow this. First of all, the introduction of authorized players for media, especially for content locked to a specific type of device, like a TV, a Blu-ray player, or a game console. The device cryptographically authenticates itself in order to decode the content. Authorized viewers, similar cryptographic authentication and decoding, but for software players like the Netflix app on your phone, or the ebook readers and as a software application. Social DRM, or watermarking, that is the content is embedded with a watermark and then distributed in an attempt to discourage its distribution, since all copies will embed the information of the person that distributed it. You might see this sometime when you're purchasing some licensed study materials, for example, or lab guides or something like that. The PDFs in there, on every single page, they have your name in there, right, as a stamp, or at least in the header or the footer. And finally, online checks, especially used with software products and video games that call home or need to be always online to work, or at least periodically, right? To check their vendor servers, to validate their running instance, or even rely on techniques like de novo for video games, where the game is shipped actually lacking some critical piece of code. Without that critical piece of code, that gets automatically downloaded specifically for your current machine when the product is authenticated with the vendor's servers. That's why de novo is tough to break. So that's the story about technical controls. Of course, we haven't talked about all the technical controls. We do have a ton of videos before this one that talk about additional type of controls, but try to remember at least the controls that we mentioned as far as access control goes, especially remember file system permissions, understand encryption, DLP, and the de-identification controls that we talked about. All right, so I hope you found this useful and informative. This time we're going to continue this topic on the next video when talking about non-technical controls for securing data. But until next time, thank you for watching, like and subscribe, and good luck. Bye-bye.